Imagine a world where the very fabric of materials can be manipulated at the quantum level, unlocking extraordinary properties that could revolutionize technology. This is not just a dream. It's the exciting reality, unveiled by researchers at Columbia University, who have discovered a groundbreaking method to engineer quantum materials by tapping into the chemistry of atomic orbitals. This innovative approach reveals a new source of frustration, a term that describes the complex behaviors of electrons in certain materials that leads to fascinating quantum phenomena. In a recent publication in Nature Physics, the Columbia team shared their findings, which challenged the long-standing notion that the geometry of crystal lattices is the sole determinant of quantum behavior. Instead, they highlight how the chemistry of atomic orbitals can play a pivotal role in creating materials with desired quantum characteristics. This shift in perspective opens up exciting avenues for designing materials that could have significant implications for various technologies. The research team, which included experts from both physics and chemistry, focused on a novel material known as PD5-ALI2. This is a classic Columbia story. Different groups in physics and chemistry collaborated to investigate this new material, leading to some thrilling discoveries about electron movement, said Aravind Devarakonda, an applied physicist at Columbia Engineering and the lead author of the study. Traditionally, the concept of frustration in quantum materials has been closely associated with geometric arrangements. In classical physics, electrons repel each other, but in certain quantum contexts, they can be compelled to pair up, resulting in remarkable phenomena such as superconductivity or unique magnetic behaviors. This pairing typically occurs when electrons cannot achieve a stable, low-energy state due to the arrangement of atoms in the crystal lattice, particularly in geometrically complex structures like triangles or squares. However, such geometrically frustrated materials are relatively rare. Enter PD5-ALI2. A metallic material that is stable in air and can be thinned down to atomic layers. Initial investigations suggested a simple lattice structure, but Devarakonda's early measurements revealed an electronic characteristic indicative of a geometrically frustrated arrangement known as a Lieb lattice, which consists of squares and has mostly existed in theoretical discussions until now. The pivotal moment came when theoretical physicist Raquel Queiroz linked Devarakonda's findings to the material's chemistry. They discovered that the atomic orbitals, regions where electrons are most likely to be found around an atom, combine to create a checkerboard pattern that mirrors the geometry of a Lieb lattice. We've uncovered a completely new way to conceptualize frustration, merging the perspectives of chemists on chemical bonds with those of physicists on crystal lattices, remarked Columbia chemist Xavier Roy, whose lab was responsible for synthesizing this new metal. This insight indicates that the material's internal chemistry, rather than just its external atomic layout, drives the complex motion of its electrons. One of the most intriguing features identified by Devarakonda was the presence of a flat band in the electronic structure. Flat bands are unique because they force electrons to occupy the same energy level, creating a state that is both unstable and rich in potential for unusual quantum behaviors. This configuration is particularly promising for the pursuit of high-temperature superconductivity, a coveted goal in materials science that could transform energy transmission and storage. The ability to induce frustration through the arrangement of atomic orbitals presents a powerful new strategy for scientists. This method offers a more straightforward and potentially more accessible route to creating materials with flat bands, moving beyond the constraints of rare geometrically frustrated structures. The Columbia team is already exploring the implications of this discovery. Devarakonda is experimenting with the material by physically stretching samples to investigate ways to control and enhance these quantum behaviors. As a layered crystal, PD5-ALI2 can be reduced to a single atomic layer, paving the way for innovative combinations with other two-dimensional materials to engineer entirely new physical phenomena. Its metallic properties and stability in thin layers are particularly beneficial, enabling the creation of more compact stacked structures. The potential applications stemming from this research are vast, It could lead to the development of advanced quantum sensors capable of detecting subtle environmental changes by leveraging the properties of trapped electrons, such as their spin direction. Additionally, insights gained from studying PD5ALI2 could aid in the creation of rare earth-free magnets that operate at room temperature, addressing the increasing concerns regarding the cost and availability of rare earth elements essential for modern technologies like electric motors and wind turbines. While PD5ALI2 itself may not be the most affordable material, the researchers are optimistic about utilizing artificial intelligence techniques to quickly identify other crystals that might exhibit this intriguing orbital frustration within their chemical bonds. The theoretical possibility of frustrated hopping from orbitals has been discussed for years, but now we have a tangible example, Devarakonda noted. There are countless models that have been proposed over the decades, but with our new understanding of lattices and orbitals, we can approach these ideas from a fresh perspective. But here's where it gets controversial. Could this new understanding of frustration in quantum materials lead to unforeseen consequences in the field of materials science? What do you think? Are we on the brink of a new era in quantum technology, or are there risks we need to consider? Share your thoughts in the comments.